Buenos días, mi nombre es Mayerlin Camargo Sarmiento y les voy a hablar de la volatilidad financiera. Tomado del artículo del autor Fulvio Corsi, lleva por título un modelo simple aproximado de memoria larga de la volatilidad realizada. En resumen abstracto, es un modelo cascada aditiva de volatilidad en distintos horizontes. Reproduce memoria larga y gruesa y autosimilitud. En el modelo Hard Additive Volatility Cascade reproduce memoria larga y similarity. La introducción. Los datos financieros muestran persistencias gruesas y largas. Modelos estándar y no capturan estas propiedades. Los datos de finanzas persisten en modelos de captura y properties. Aquí les voy a mostrar unas fórmulas del modelo que es beta sub d, beta más beta sub w, son 3 escalas temporales y que me dan el resultado de la volatilidad realizada en días futuros. Las notaciones son volatilidad integrada y realizada y agregaciones semanales 5 días y mensuales 22 días. Bueno, aquí habla de motivación. Hay motivaciones muy corto plazo, mediano plazo y largo plazo. Hipótesis de mercados heterogéneos, cascadas de horizontes largos hacia cortos. Dice, aquí vamos a explicar lo que es heterogéneos autoagresivos en Excel, pero les voy a mostrar un pequeño video.
But you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and I'd also greatly appreciate if you consider sponsors as well. So click to the link in the description or click the join button below for more details. My name is Sava, and today we're investigating a very interesting and elegant in its simplicity, yet somewhat understudied and underappreciated, in my opinion, volatility model, which is the heterogeneous autoregressive volatility model, or HAR for short, first developed by Corsi relatively recently in 2009. This model has the advantage of not relying on maximum likelihood to be estimated. It can be estimated using OLS, quite strikingly. That's very untypical for volatility models. And it is also very straightforward in terms of forecasting volatility over various future time horizons. It also demonstrates reasonably good fit compared to other volatility models, primarily various Gauge extensions, and it takes advantage of either open high-low close candles, which are quite commonly used for more information to be presented in terms of the dynamics of the market, or more frequently nowadays using intraday high-frequency data, for example, minutely, hourly data that has become recently available in the modern day of age for most financial markets of interest. In this video, I'll present an application of HAR based on OHLC candles. However, if you would like me to do so in the future, please leave a comment, and I'll also do an implementation based on intraday high-frequency data. The idea is to relate the variance, realized variance, at a particular day to the unconditional component omega. Here is where it borrows directly from the Gauge specification, nothing wrong about that. The lagged realized variance in the previous day, as well as average realized variance over the past week, and average realized variance over the past month. Corsi here proposes that you do not need to implement too much lagged terms to capture most of the relevant conditional variance dynamics, as realized variance could be explained as, a quantity dependent on realized variance yesterday, realized variance last week, and realized variance last month. You do not need to overcomplicate the model more than that. And that's the beauty of the HAR model, the beauty in its simplicity and the intuitive content that it has. So for the estimation, we first need to calculate realized variances for the sample days. We have got S&P 500 data for a 10-year period from year-end 2012 until year-end 2022. We'll seek to estimate the HAR model and then forecast the variance of S&P 500 50 days ahead. And for the realized variance proxy, we'll use the Parkinson variance estimator. We had a couple of videos on Parkinson volatility estimation previously, including its definition and also its application to market efficiency measurement. Here we're using it as our input, as our measure of realized variance. We need to calculate the logarithm of high price divided by low price squared and perform the common adjustment, which is 4 times natural logarithm of 2 in the denominator. That allows us to calculate the realized variance in a particular day. However, this is a very small number, given that our variance is daily and it is a squared term, isn't it? So to make it a little bit more interpretable and so that we don't have to look at too many decimal places, I suggest multiplying it by a factor of 10,000, which is 100 squared. So here we will effectively be looking at percentage variance, the variance of return in percentages, which is also quite understandable and which generates a number that's much easier on the eye. We apply it all the way throughout. Here we have forecasts, so we can delete the errors that are associated with the fact that we don't know the prices for the future. We'll seek to fill those in with our hard model output. And now we need to estimate our realized variance in the previous day. We can do it using a simple lag operator.
Los colombianos que abran una cuenta de 430.000 pesos antes de fin de mes podrán ganar fácilmente 12.000.
And apply throughout. Then we can calculate our realized variance over the past week. A week is 5 trading days on average, so we can see where we have got 5 realized variances estimated. Over here we have got 5 lagged realized variances, so we can calculate the average of those 5, and again apply throughout. And then we need the realized variance in the past month. Here we have got quite a curious observation. Corsi himself developed this for European markets, where you've got less weekends generally than on the US markets. So Corsi suggested we choose 22 trading days, as there are more typically 22 trading days in a European trading month. We'll stick with that, but if you are using US data, you can always go for 21 as your measure of choice for the number of trading days in a month, and therefore your lag length for calculating the average realized variance in the past month. So here we can see when do we get 22 days for the first time to calculate our average, and this is the first day where we can. So we calculate it across 22 previous trading days and enforce it throughout. And then we can simply delete the errors associated with forecasts that we do not know the projected realized variances yet. And for this very reason, we can estimate the HAR model. we can select a 4 by 5 range, so there are always 5 rows in the Linus template. And we've got 3 explanatory variables plus the constant. Again, constant is the unconditional variance, and we've got daily, weekly, and monthly lagged realized variances as our explanatory variables. So we can enforce the Linus function, select the realized variances from the day we can first calculate all the explanatory variables until the very end, and we can select our 3 explanatory variables as our x variables. We input 1 as we do on the constant, that's our unconditional variance, and we want the additional statistics to perform significance test. Then we enforce this using shortcut enter, and we get our Linus template in front of us. For t-stats, we can divide the coefficients by the respective standard errors, and we can perform usual 2-tailed t-distribution significance testing for the coefficients, plugging in the absolute values of t-statistics and the degrees of freedom, which are the same across all tests, so we log them. And dragging it across, we see that there are very significant effects of daily and weekly realized variance, so persistence is captured in this case. The coefficients are also quite intuitive. They are of very typical magnitude to what you would see in an application of an arch model or a gauge model. However, there is little to no persistence on a monthly frequency. So volatility persistence or variance persistence dissipates more quickly than a monthly average realized variance can take off. So our variance persistence is actually more short-term than the Corsi specification presumes. However, we still got very significant effects for daily and weekly, and we can see that the R-squared is 0.63. We explained 63% of variation in our realized variance using such a simple specification, which is obviously very good news. Now, in terms of the forecast, we can quite easily drag the like daily, like weekly, and like monthly formulas one step ahead, because they would still refer to the real-world data. They would not refer to any empty sets. That means that we can perform the one-day ahead forecast very naturally without making any extra assumptions, without feeding in other forecasts into the model, which is what some volatility models seek you to do. So one-day ahead forecast would involve adding to the constant that we just estimated for the HAR model, 1 day lagged realized variance times by the respective coefficient that we have to log, plus the 1 week lagged realized variance, and we can multiply it by the respective coefficient logged, and finally monthly average realized variance times the respective coefficient logged. And then this can be automated all the way down, and we can see how our forecast.
Los colombianos que abran una cuenta de 430.000 pesos antes de fin de mes podrán ganar fácilmente 12 millones.
Evolves over time. There is some notable convergence. At some point, these values will all converge to the long run value of our realized variance. This is the property that is quite standard across different classes of variance or volatility models. However, we see some quite interesting dynamics here with 1 day realized variance directly feeding off to the forecast, and the more long-term figures still picking in a range of real-world values before they also converge. This is a very welcome property of the HAR model, as it allows to model quite complex variance dynamics with a very easy and simplistic toolbox. However, it also has a number of limitations. First of all, it's as good as your estimator of realized variance is. If you don't believe something like the Parkinson volatility estimator, you cannot fully trust the output of the HAR model. Using intraday data for this is a little bit more precise, a little bit more favorable. Next, there is some bias involved in the estimation of realized variance, and this is what further extensions of the model, such as the HAR-Q model that also introduces realized quanticity, so higher moment measures, into the estimation. This is what these models seek to address. They are a little bit more complicated, a little bit less straightforward, and again, a little bit less straightforward in terms of forecasting. However, they do address the biases that are associated with measurement errors for realized variances. However, this model is still a very useful and underappreciated tool for variance modeling. Please leave a like on this video if you found it helpful. In the comments below, I'm going to.
Ok, como pudimos evidenciar, explicamos la volatilidad larga
The first suggestion for videos in business forms economics with leverage report.
La volatilidad larga y la forma de accesible de los fundamentos de lo que es la regresión, la acción regresiva. Ahí en ese video mostramos una estructura básica del modelo y sus componentes de la volatilidad en diferentes horizontes. Ahora aquí vamos a mostrar la simulación, la reproducción de colas gruesas, autocorrelación persistente. Aquí en esta imagen estamos dando como el análisis empírico, los datos y la estimación vial. Aquí en esta diapositiva hay una imagen que son los tres horizontes significativos, que están una incidencia que están las betas con la sub D, sub W y sub M. Estas significancias estadísticas semanales y mensuales en el modelo HAR. Las barras muestran los coeficientes de las betas y las líneas punteadas indican el nivel crítico de significancia. Ahora aquí vamos a hablar del pronóstico. HAR muestra aquí que supera consistentemente a AR1 y AR3 y muestra un desempeño comparable con AR y excelente propósitos a un día y una semana 2. ¿Qué más le puedo decir acá? Bueno, en conclusiones, es un modelo simple, efectivo, extensible, con una excelente capacidad predictiva. Aunque no es fundamental, no es formalmente un modelo de memoria larga, HAR logra replicar muy bien las propiedades típicas de procesos largos y la clave está en su estructura. Es multinivel, usar la volatilidad agregada a diferentes horizontes, crea un efecto pseudo de memoria larga, con un comportamiento muy similar al real, sin necesidad de operadores fraccionarios, kernels complejos ni estimaciones pesadas. Su fundamento es la hipótesis de mercado heterogéneo, es teóricamente sólido e empíricamente compatible. El modelo está inspirado en la idea de que los agentes operen con horizontes distintos y evidencia clara de que las volatilidades de horizontes largos empujan a los horizontes cortos, pero no al revés. En conclusión, el HAR integra economía de comportamientos, microestructuras y estadísticas en un marco coherente. La parsimonia del modelo en un largo técnico significativo. Muchos modelos que intentan capturar la dinámica de volatilidad requieren estimar decenas o cientos de parámetros. HAR3 logra resultados comparables con solamente 3 betas y un intercepto. Este resultado refuerza la idea de que la simplicidad no solo deseable, sino que puede ser óptimo desde un punto de vista predictivo. Aquí sus resultados de pronósticos son sorprendentemente robustos con múltiples horizontes. El HAR3 supera consistentemente a AR1 y AR3 y se comporta muy similar a ARFIMA, incluso en pronósticos exigentes como la semana 1 y la semana 2. Esto es notable porque ARFIMA captura memoria verdadera y HAR solo replica memoria de manera aparente. Es un modelo con enorme potencial de extensión aplicable a contextos reales de riesgo de finanzas. Plantea varias extensiones, incluso saltos, efectos de apalancamiento y modelos no lineales, versiones multivariadas al vector HAR. Esto lo convierte en un modelo vivo, adaptable a riesgos sistémicos, volatilidad de portafolio y derivados, análisis de contagio. El artículo tiene un impacto metodológico importante en la econometría moderna. Muchos modelos que intentan capturar la dinámica de la volatilidad requieren estimar decenas o cientos de parámetros. En HAR3 logra resultados comparables con solamente 3 betas y un intercepto. Este resultado refuerza la idea de que la simplicidad no solo es deseable, sino que puede ser óptima desde un punto de vista predictivo. Y ya para concluir, el modelo simple aproximado de memoria larga propuesto constituye una alternativa práctica y parsimonia para capturar la dinámica de la volatilidad realizada. Su estructura minimalista permite emular la persistencia característica de los mercados financieros sin recurrir a modelos fraccionales complejos. La facilidad de estimación y adecuada capacidad predictiva lo hace especialmente útil en aplicaciones operativas donde la simplicidad y la rapidez son fundamentales. Este enfoque ofrece una herramienta poderosa para análisis financiero y gestor de riesgos que requieren modelos transparentes, robustos y fácilmente implementables. Muchas gracias.